Okay, so let us begin our class today. Today we'll be doing chapter 12. Chapter 12, oops. Yeah. Okay, chapter 12 is heat conductions and also thermal expansions, in which it means this chapter it contains two main subtopics. One is about conduction and the other one is about expansion. So first we'll be looking at the 12.1 heat conduction. Now, what is heat conduction? Basically, you have only one main equation in this chapter, which tells you the rate of heat transfer. So when you talk about the rate, then we use dq over dt. We use the energy divided by time, which is equals to negative ka dt over dx. Okay, now we have to know what does it mean by these equations. So dq over dt, it tells you how fast the heat energy is being transferred in a conductor. All right, so heat is a form of energy. It has nothing to do with the degree of hotness. If you want to know whether something is hot or is cold, we look at its temperature. So don't get confused between the heat and also temperature. They are two different things. Heat is energy and the unit is in joules. And then temperature, it tells you the degree of hotness. Whether something is hot or is cold, it's based on your temperature. Okay, and the unit, the SI unit is Kelvin. So now we have dq over dt, which tells you the rate of heat transfer equals to negative ka over dt, ka dt over dx. So k is your constant. Okay, it is the thermal conductivity. So higher k, greater k means it is a better conductor, and A is the cross-sectional area. And dt over dx is the temperature gradient. Okay, temperature gradient. So you need to know the meanings of these equations. So this is the only equations that we have basically in this first subtopic. And then another thing that you have to know is what happens in a steady state. Okay, so initially when you heat up something, maybe the heat flows on the hot end and the cold end, they are not the same. So this is a rod. So when it just begins to heat up something, let's say, so the heat flow, okay, might be not constant, okay, not uniform. But at one point, the rate of heat transfer will be constant at every single point along this road. Okay, and at that moment, we call it steady state. Okay, and if you have two joint roads, okay, let's say now you have a road A and then road B, you join them together and then you put an insulator around them. When this road is in steady state, then what can we say about it? Well, dq over dt in road A would be equals to the dq over dt in road B. Okay, both of them, they will have the same rate of heat transfer, okay, when they are in steady state. So most of the times, if you look at the questions will tell you now something is flowing, something has a rich steady state, and then it asks you to calculate maybe the temperature, the final temperature, the initial temperature, the hot end, the cold end, and so on, right? And then there's one more thing in the equation, which is the negative sign. Negative sign, it just tells you now your heat transfer is flowing from high temperature towards lower temperature. Okay, so dt over dx, in other words, dt over dx is always a negative value. Okay, because our final temperature is the cold end and the initial temperature is the hot end. So T final minus T initial over the length, okay, dx. So T final, usually it refers to hot end, cold end, and then T initial, it refers to hot end. Because heat, the energy is flowing from hot end towards cold end. So that is the things that you need to know, all right? So because dt over dx is a negative value, so it will cancel out the negative sign in the equations. Therefore, dq over dt, the heat transfer, the rate of heat transfer, is a positive value, all right? Oops. So now let's look at questions 1. Okay, so the summary is just very short, just about these equations, how to use it, and what is the crucial part that you have to know in the equations. So now questions 1. A major source of heat loss from the house is through the windows. So we have a windows right here. Calculate the rate of heat transfer, heat flow through a glass window of 2 meter by 1.5 meter in area and 3.2 mm thick. So you have to know which surface area is in contact directly with the heat. Okay, it's the large area, it's the big surface area, not the thickness. So make sure you don't use the wrong A. Okay, because cross-sectional area is a surface area that is in a direct contact with the source of heat. All right, so when it comes to window, of course, it's a large surface area. Okay, it's the large surface area here. It's not the thickness. So if the temperature at the inner and at the outer surface is 14 and 15 degrees respectively, so calculate the rate of heat flow. So rate of heat flow, we have dq over dt equals to negative Ka dt over dx. Okay, so now I'm going to expand the equation. So I have negative Ka T final minus T initial over dx. So what am I going to do next? Okay, now let's see. I think one thing is missing from the questions. Okay, the K is missing. Okay, so K in this question, now because you have a glass, if you look at the table on a page, see which page, yeah? You have the books, you look at the table on a page 267, okay, 267, then you have the K for glass is 0.8. Okay, if you look at the lecture notes, okay, the lecture notes, chapter 12. So in this table, now don't worry, you don't have to memorize it, okay, you don't have to memorize it. You just have to know this value because now this is an exercise, so you have to refer to the table. In your exams, the value will be given. So don't worry, okay, don't have to memorize it. I will repeat, don't need to memorize the value. So this is an exercise, that's why you need to refer to the table given in your books. So you look at this page of 214, okay, your book is 214. Page 214, K is equal to 0.8. So now I have K is equals to 0.8. Okay, so I'm going to write it here, somewhere here. Okay, so K equals to 0.8. And then, okay, the unit is a Wm negative 1, K negative 1. Okay, so thermal conductivity. And then what do I have? Okay, I need a surface area. So the surface area is the large surface area here. So A is then equals to 2 times 1.5, which is equals to 3 meter square. Okay, 3 meter square. And then what else do I need? Now I need the thickness. So in this case, thickness is my X. All right, X is the thickness. So my X is now equals to 3.2. Now make sure everything is in SI unit because you want to calculate the rate of heat transfer. Okay, the energy in terms of joule. So 3.2 times 10 to the power of negative 3 meter, that is your X. So now we have the temperature. We are given two temperature. One is a 14 degree and one is 15 degree. So we need to know which one is initial, which one is final. So if you remember, okay, I told you just now, the heat is always transferred from hot end towards cold end. Okay, hot end towards cold end. So what are we going to do? So which means the hot end is our initial temperature, and the cold end would be our final temperature. So when you sub it into the equations, what are you going to do? It should be 14 minus 15. Therefore, you will obtain a negative value here. 14 minus 15 is equal to negative 1. Negative 1 and this negative, they will cancel out. So eventually, you will obtain a positive value that is equal to 750 joule per second. All right, because you are calculating the rate. So need to have a S negative 1 right here. So this is the way to solve questions 1. Okay, this is how you solve questions 1. So now I give you 1 minute to write it down. Make sure you take notes on where is the initial and where is the final. Where is the cross-sectional area? Cross-sectional area is the part that is in direct contact with the heat. Okay, so in this case, it's the large surface area right here, not the thickness. Okay, not the thickness. So 1 minute for you to write it down. Make sure you take notes on where is the initial, where is the final, and how to calculate the cross-sectional area. All right. So now let's look at questions 2. So questions 2. Wait, yeah. Okay. All right. So questions 2, one N properly insulated copper rod of a length 20 cm and cross-sectional area 2 cm square is maintained at a constant temperature 100 degrees C, while the other end is at 0 degrees C. If the rod is in steady state, determines the temperature gradients along the rod. So now you are given a rod. Okay, so one end you put it at 100 degrees C, and the other end is 0 degrees C. The length of the rod given, L is equals to 2 cm, and then given cross-sectional area, which is the area right here. This is your cross-sectional area. So A is equals to 2 cm squared. All right, 2 cm squared. So calculate the temperature gradient along the rod. So questions A, temperature gradient is dt over dx, which is very simple. So dt over dx, it is equals to your T final minus T initial divided by the length. Okay, divided by the length. So now let's look at the questions again. Where is initial and where is final? Remember, hot end is the initial. This is your initial. And the cold end is your final. This is your final positions, final temperature. Therefore, we have 0 minus 100 divided by 2. Okay, so it is then equals to negative 500. Okay, 500. Sorry, it's not 2, it's 0 0.2. Okay, 0.2 cm, 0.2 meters, sorry, 2 cm, 20, no wonder. So the length is 20 cm, not 2 cm, my bad. So 20 cm is 0.2 meter. So dt over dx is then equals to negative 500 degrees C m negative 1. Okay, degrees C m negative 1. So that is the answer for questions A, temperature gradient along the road. And then questions B. Okay, now let's look at questions B. Questions B asks you to calculate the temperature at a point 4 cm from the hot end of the rod. So now what you want is no longer the 20 cm. What you want is just 4 cm. So maybe you would want to take here as a final position right now. Okay, so final positions, I'm going to change the color to make it easier for you. So now let's say now this is 4 cm, and then this will be the final position for questions B. Okay, so what am I going to do right now? I will have dt over dx. Again, it is equals to T final minus T initial over L. Well, because the rod is in a steady state, therefore the temperature gradients along the rod is constant, it's the same. All right, therefore I have dt over dx is equals to negative 500. Now my hot end is still 100 degrees C, And cold end, I don't have the information about the cold end. Therefore, I don't know what is my T final right now. So I'm going to keep TF here minus the initial. Initial is still 100. So minus 100 divided by the length. The length is no longer 20 cm. The length right now is just 4 cm. Okay, because now if you look at the question, it tells you you are looking at a point that is 4 cm from the hot end. So L is now 4 cm, which is equal to 0.04 meter. Okay, 0.04 meter. So rearrange the equations. Eventually, you will obtain T final is 80 degrees C. Okay, so the point that is 4 cm, okay, the 4 cm from hot end, the temperature is 80 degrees C. So 20 cm, you got 0 degrees C. 4 cm, you got 80 degrees C. So you can use the same method to calculate the temperature at any point from the hot end or any point from the cold end. As long as you know the value of the hot end and also the cold end, then you should be able to determine the temperature at any point in between these two ends, right? So now let's look at question C. So question C, it asks you to calculate the rate of heat flow through the rod. So now you want to calculate the rate of heat flow of the whole rod. dq over dt is then equals to negative Ka and then T final minus T initial over L. So you can use the value from questions A. Okay, so it is equals to negative. Now given K is 380 and then cross-sectional area given is 2 cm square. Now 2 cm square is not 0.02 meters square. It is 2 times 10 to the power of negative 4 meters square. Okay, and then dt over dx from questions A is a negative 500. Okay, because now you're looking at the whole rod. Therefore, we look at the value from questions A. So it is then equals to 38 joule per second. Okay, 38 joule per second. So remember, 20 cm, 2 cm square, 2 cm square is not 2 times 10 to the power of negative 2 meters square. It is 2 times 10 to the power of negative 4 meters square. Right? So if you forgot how to do the unit conversions, you can do a revisions in chapter 1. All right? So I've already explained how to obtain this value in chapter 1. So if you forgot how to convert it, then you have to do revision. All right? You have to go through the revisions again. So this is the answer for questions 2. Now I give you 2 minutes to write it down. Okay, 2 minutes untuk anda catat jawapan ini. So make sure to take notes, especially the questions B. Okay, questions B, the negative 500. Now because it is in a steady state, so every point along the road they have the same dt over dx. Okay, they have same dt over dx. So 2 minutes for you to write it down before I proceed to the next question. right, so let's look at next questions. Next question, now you have two joint roads. Okay, if you look at the questions. So two properly insulated uniform roads. Now, uniform roads means that now both D and E, they have the same cross-sectional area. Okay, they have same diameter. So two properly insulated rods, D and E, they make a thermal contact at one end as shown in figure. So when it comes to this question, the part that you have to take note is where is the initial for rod D, and then where is the final for rod D, as well as where is the initial and where is the final position for rod E. So now that you have two rod, one D and one E, when it comes to rod E, the initial position is the 100 degree and the final position is 80 degree. Okay, when you have two joint rod question, this is a part that you have to take note, the initial and the final position. When it comes to rod E, the initial position is 80 degree. It is not final positions anymore, okay? It is a final for rod D, but it is acting as initial for rod E. And then the final for rod E is the unknown T, all right? So now that I have a rod D and rod E, so D and E, they have different set of information. They have different initial and different final position. So the cross-sectional area for both rods, they are the same. And the rods, they are in a steady condition. So steady condition, it means dq over dt for rod D, it is equals to dq over dt for rod E. Okay, that is the purpose of the term steady condition in the questions. So it determines the temperature gradients along rod D. So now you want temperature gradient for rod D, dt over dx for rod D. Okay, dt over dx for rod D, it is equals to T. Okay, now T, what am I going to call it? I'm going to call it, because it is a joint place. So what am I going to do right here? Now to make it easier, I want to give three different labels. So hot end, 100 degree, I'm going to label it as a ND. The joint end, okay, the joint, the place that are in contact with each other, I'm going to call it DE. And then the cold end, the unknown, I'm going to call it E. To make it easier for me to write a subscript in my equations. So now dt over dx for rod D, the final temperature, like I told you just now, is the 80 degree position. So TDE, okay, minus the initial, which is TD, divided by XD, okay, the length of rod D. So I like to use subscript in my equations, okay, to make it easier for me to recheck, okay, when I want to check the answer, okay, to go through the answer again. So always use subscript to make it easier for you to recheck your answer. Okay, and it's easier for you to identify the mistake in case you make any careless mistake in your calculation. So TDE minus TD over XD, so it is equals to 80 degree minus 100 divided by now 20 cm, 0.2 meter again. So it is equals to negative 100 degrees C m negative 1. So that is the answer for questions 1. Okay, that is the answer for questions 1. Now, how about questions 2? Okay, questions 2, the temperature at the free end of rod E. So now questions wants you to calculate the temperature here, the unknown T. So what should you do? Now, because the question tells you they are in a steady condition, steady state. So what I do know now is dq over dt. D is equals to dq over dt, and then E. Okay, dq over dt for E. So what am I going to do right now? Okay, now I want to expand the equations. So dq over dt for rod D, so negative kd. Remember, K and the temperature gradient, okay, K and dt over dx, these two variables, they depends on the material. Okay, so you need to include the subscript when you expand the equations, because root D and root E, they will have different K, different thermal conductivity, and also different temperature gradient, because now you're looking at different root. So negative KD and then A. Now A, I don't need to put a subscript. Why? Because both of them, they have the same cross-sectional area. Okay, they have the same cross-sectional area. So, and then a dt over dx for root D, and that equals to negative ke a dt over dx root E. So what I'm going to do next, I'm going to cancel out the variables. Okay, the variables, the same variable for both root, which is the negative sign, I can cancel it out. And then A, I can cancel it out. Okay, so next, I want to include the value. I want to expand the equations. So KD, according to the question, is equals to K, and KE is equals to 2 over 3K. So I'm going to substitute K right here. dt over dx for D, I have the value already from questions 1. So negative 100 is then equals to, now KE is 2 over 3K. So 2 over 3K. And then, now dt over dx for root E, T final is my TE, right? Minus TDE divided by XE, okay? The length of root E. So when you compare the equations for dt over dx in the questions 1 and the one in questions 2, you will see that the subscript, they have different subscript here. That's why I asked you to include the subscript so that you know which value to use, okay? You know which value to use. So negative K negative 100 is equals to 2 over 3K bracket TE minus TDE over E. Again, I can cancel out the similar terms on both sides, which is K. So now I can remove the K from my equations because both sides, both left-hand side and right-hand side, they have the same variables. Right, so after I remove it, I can then simplify the equations. Negative 100 is then equals to 2 over 3. Now, TE, I don't have the value, so I want to keep it as unknown. TE minus DE. So DE, according to the diagram just now, I have 80 degree. So divided by 40 cm, 0.4. So rearrange the equations. Eventually, you will obtain TE is equals to negative 20 degrees C. Okay, negative 20 degrees C. All right, so negative. Yeah, okay, so that is your answer. So temperature at cold end is a negative temperature, so it's very cold, right? It's very cold. So negative 20 degrees C, that is your final answer. Is it negative? Let me rearrange the equations. Something is wrong. So 100 times 0.4, you obtain 40. Okay, 40 times 3, 120 divided by 2, 60. So 60, you have here, negative 60. Now it should be positive, okay? The final answer in your book is wrong. It should be positive. Because if you rearrange the equations, negative 40 equals to 2 over 3, TE minus 80. So here you will have negative 60. It is then equals to TE minus 80 degrees. So rearrange TE should be equals to 20 degrees C. Okay, so final answer in your book is wrong. So it is a positive 20 degrees C. Okay, positive 20 degrees C. So that is the answer for questions A2. Okay, that is the answer for questions A2. So now I give you 2 minutes to write it down first before we go through how to sketch the temperature gradient graph. Right? So I give you 2 minutes to write it down. Make sure you know how to simplify the equations. Okay, the variables that can be cancelled out, the variables that you have to keep it in your equations when it comes to question number 2. Alright, soalan 2 kamu kena tengok unknown mana yang kamu boleh cancel dan kenapa. Dan yang mana satu Anda tak boleh cancel dan juga kenapa. That is very important in this subtopic. Okay, in this subtopic. So 2 minutes for you to write it down before we go through the graph questions. Okay, so now let's look at questions B. Questions B, okay, for this question is easy. Okay, why? Because you are given all of the value. So you have the value as hot end, you have the value as cold end, you have the value of a joint end, the place that are joining together, and then you also have the length. Now, what if, okay, what if in case you are not given any of the value? So what you should check is that you have to look at the K. So since KD is larger than KE, and we know K is inversely proportional to dt over dx. So what does it mean? It means dt over dx for D, it should be smaller than dt over dx for E. Okay, so which means which one is steeper? If you look at these two values, the root E should be steeper compared to root D. Okay, dia lebih cerun untuk root E kalau berbanding dengan root D because of this equation. Okay, because of this one. So when it comes to graph sketching, if you are not given the value, then you have to check which one have larger dt over dx. Okay, so now the question asks you to sketch a graph of t against x. So t is right here. This is degree C. And then x is here. So you put in terms of meter or cm, it's up to you. All right, make sure you just have the right label. So when it comes to this question, it's very simple because you are given the value. So this is 100 degree. This is 80 degree. And then the co-end, according to questions A2, is 20 degree. So 20 degree should be somewhere here. Now, when it comes to graph sketching, you don't have to follow the exact scale, okay? The proper scale. Just roughly sketch the value. So here's 0, here's a 0.2, here is 0.6, okay? Agak-agak sudah cukup. Dia tak payah ikut nilai yang sebenar because it's just a sketching, alright? Unless the question asks you to sketch according to the scale, then you have to measure the length. So when it comes to graph sketching, the things that you need to have in your graph is just the axis, the label of the axis, and then the value because you are given the value and you have to have the right shape, okay? Right shape. So first part, root D is from here to here. And then, okay, it's too steep. So it should be some things like this. And then, okay, it's a steeper. Okay, so make sure it's joining together. So from 100 to 80, less steep. And then from 80 to 20 degree is much steeper. Okay, so tak sampai hujung. It should be somewhere right here. So, okay. Okay, so you need to put a dotted line here to indicate the part for different road. So from 80, from 100 until 80, okay, from 100 degree drops to 80 degree, which is from 0 until 0.2 meter. This is for your road D. Okay, and then this is for road E. So D and E, as you can see here, E is steeper compared to road D. Now, of course, you don't need to put a dot, okay? You don't need to put a dot here. I just put it here to shows you the joint end. Okay, tak payah letak dot di sini, tak ada masalah pun. Alright, saya letak dot di dalam example ini untuk tunjuk Anda joint end mereka, okay? Di bahagian mana sampai D, bahagian mana adalah permulaan E, road E. Okay, so in your actual sketching, don't need to put dot, okay? Don't need to put dot. So that is the answer for questions B. Okay, so this question is easy because you're given all of the value. You just have to sketch it according to the value. But in case you're not given any of the value, then this is how you solve it. Okay, this is how you solve it. So you look at the dt over dx, see which one has a larger value, means it is steeper. Okay, means it is steeper compared to the one with a smaller value. So I show you both methods just in case. Okay, just in case you are not given the value. So now I give you again 2 minutes to write it down and then make a short note on how to solve it if you're not given any of the value. Okay, sama juga bagi Anda 2 minit untuk catat dan buat catatan. Sekiranya Anda tidak diberi sebarang nilai, apa yang Anda kena buat? Okay, so the box on the left hand side, that is how you should solve it. Okay, so that's it for questions number 3. So now let's look at questions number 4. Again, questions number 4, if you look at the question, it is a joint road types questions. Okay, it's a joint road types questions. So we have a copper plate of thickness 1 cm. It's a sealed to a steel plate of thickness 10 cm as shown in figure here, as shown in figure. So according to the questions, the temperature of the exposed surface of the copper and the steel plates, they are 30 degree and 15 degree respectively. And then given K copper is 385 and K steel is 50.2. determines the temperature of the interface between the couples and the steel plate. So now you have a hot end here. I'm going to call it a TH right now, hot end. And then the steel, I'm going to call it cold end, TC. And then the joint end, I'm going to call it TJ. Okay, TJ. So TH, TC, and TJ to make it easier for me. So now the questions ask you to determine the temperature of the interface between copper and the steel plate. Meaning that it is asking for the temperature at the joint. Temperature at joint is an unknown. So what should we do? Now, the only things that we can use to join these two together is the equations at a steady state. All right. So which means now we're going to determine dq over dt for copper, which is a C copper. It is equals to dq over dt for steel. Okay, this is the equation that we're going to use because we want to calculate the joint temperature. And joint temperature is an unknown. When it comes to unknown, most probably, okay, you will need to use these equations, okay, at the joint end. So dq over dt is copper. Now I'm going to expand the equation. So negative K copper, and then the cross-sectional area. Now, if you look at the diagram, two of them, they have the same cross-sectional area. Okay, two of them, they have the same cross-sectional area. So I'm going to leave it as an A without subscript. And then dt over dx. Now, T final for copper is now Tj, the joint. So minus TH. Okay, the hot end is the initial temperature. So divided by X for copper. It's then equals to negative K steel and then A. Now the whole end is my final. And the joint is then my initial. Okay, so divided by X steel. So if you look at this equation, the crucial part is where should you put the TJ? Okay, students always got it wrong because they placed the TJ at the wrong position. Okay, they use TJ minus TH, and then on the right hand side, again, they use TJ minus TC. That is a very common sin mistake in the exam. All right, so make sure you double check it. Make sure you put the TJ at the right position. It is acting as the final temperature for the first rod, but it is acting as the initial temperature for the second rod. All right. So now that I have the equations, next would be, okay, I'm going to cancel out the things that I don't want first, cancel out the negative sign, and then A can be removed again because both of them, they have the same cross-sectional area. Okay, next step, I'm going to include the value, substitute the value. So K copper, Kc is 385, bracket, Tj is unknown, so I'm going to keep it as Tj, minus the hot end, which is 30 degrees C, divided by the length. Now 1 cm is 0.01 meter. And then equals to K steel is 50.2, and then T cold is 15 degrees C, minus Tj. Tj is an unknown again. And then the length, 10 cm, 0.1 meter. So rearrange the equations. Eventually, you will obtain 29.8 degrees C. Okay, so that is your Tj. Okay, Tj is equals to 29.8 degrees C. So that is how you solve questions A. Okay, just very simple questions. And then questions B. Questions B, the amounts of heat flow from the copper plate to the steel plate in 1 minute if the cross-sectional area for both plates is 50 cm square and no energy lost to surrounding. Now, how am I going to solve these questions then? So in this case, you want to find out what is the energy. Okay, what is the energy in questions? So from copper, the amounts of energy flowing from copper plate to steel plate in 1 minute. So you want to know dq over dt. Okay, it is up to you which one you want to use because now you want to calculate q. If you want to calculate Q, you just choose either one. You can choose dQ over dt for copper, or you can choose dQ over dt for steel. It doesn't matter because both of them, they have same value. So let's say I want to choose dQ over dt for copper. So what I'm going to do now is negative KCA T joint minus T hot over XC. Since I want to calculate Q, okay, means that I need to use both sides of the equations. So let me expand the equation. Now, according to the question, you want to calculate the heat flow in 1 minute, the energy in 1 minute. So these equations can then be written as Q over 60 seconds, because 1 minute is equals to 60 seconds, okay, dq over 60 seconds equals to negative k, so kc is 385. According to the questions, the cross-sectional area is 50 cm squared, so it is equivalent to 50 times 10 to the power of negative 4 meters squared. And then bracket T joint, according to a previous questions A, 29.8 minus the hot end, which is 30 degrees C, divided by the length, which is 0.01. So rearrange the equations. Eventually, you will obtain the energy is equals to 2310 joule. Okay, 2310 joule. Now, of course, you can also use dq over dt for steel to solve it. Okay, same method. Then you just use negative ks and then a t cold minus t joint divided by x steel. Okay, so you can try it and eventually you will obtain the same dq. Okay, 2310 joule. All right, so basically it's the same. Okay, basically it's the same. Because of what? Because now they are in steady. They are in a steady state. Okay, because now the both rod, they are in a steady state. So even if the questions didn't tell you anything about steady state, in your syllabus you assume it is in a steady state. Okay, that is assumption in your syllabus. So now I give you okay, now it's at 8:50. Since we're done with the first subtopic, so let's take a short break. Okay, we'll come back at the 9 a.m. Okay, we'll continue again at 9 a.m. So you write it down and then you can take a short break. Let's continue at 9. Okay, so 10 minit break dari sekarang untuk kamu catat dan rehat sekejap. Okay, so let us continue with thermal expansions. Okay, so just now we look at the conductions. The heat is flowing from a higher end, from a hot end towards cold end. Now let's see what happens now after you heat something up. Okay, so the whole things now they have the same temperature at every point. So what is going to happen to that particular object? So in that case, the object they will start to expand. Okay, not a lot, just a little bit, maybe just a 0.001 cm or something like that. Okay, but still expand. Why? Because now the particles inside the object they are vibrating with a larger amplitude. Okay, therefore the length, the size, it expand a little bit. So in that case, we call it thermal expansion. So there are three types of thermal expansion that we're going to look at. The first one is a linear expansion. Now, when it comes to linear expansion, it happens only in solid object. Okay, it happens only in solid object. So if your object is solid, then it involves linear expansion. So linear, it could be a rod-like object. Okay, it could be a rod-like object. You're looking at the length. And then it could be, now you have a circle here. Okay, you have a circle here. But then you're not going to look at it as a surface area. You're going to look at it as a linear expansion. Now, if in terms of a linear expansions, we can check it. Okay, we can look at it. Okay, we can look at it the diameter. Okay, so the diameter is also a form of a linear expansion. Okay, and then if you have a square surface, square area, then the length, okay, the length, we can take it as a linear expansion as well, right? So when it comes to linear expansion, the equations, okay, the equation is just a very simple. If you want to calculate the change in the length, then you use equations, okay, delta L equals to alpha, okay, alpha, and then the initial length times delta T. If you want to calculate the change, if you want to calculate the final length, then you just rearrange the equations and eventually you obtain final length equals to initial length, bracket, 1 plus alpha delta T. So this is the equations. All right, and what is alpha? Alpha, basically, you just rearrange the equations, then you will obtain it. Okay, so I'm not going to write it down. I will just give you these two equations. So if you look at your books, there are three equations altogether, but actually alpha is coming from the first equation. You just rearrange it, and then you obtain the equations for alpha. So when it comes to the surface area, obviously, you're going to look at the whole area of the object. Okay, so area, it could be a square surface, it could be a circle, it could be a square surface, it could be a triangles, maybe. Okay, so all these, they are area. So you look at it as a whole. You're not looking at the diameter anymore. You're not looking at the length of the side anymore. Okay, so you're looking at the whole object. So when it comes to surface area, then basically you have the same equations. The only difference is the symbol that you use. So if you want to calculate the change in area, then delta A equals to beta, and then A initial, delta T. Or if you want to calculate the final surface area, A final is equals to A initial, bracket, 1 plus beta, again, delta T. So you have a different constant right here. Okay, different constant. So yeah, this is the coefficients of expansion. Coefficients of a linear expansion is alpha. Coefficients of an area expansion is a beta. When it comes to volume, of course, you can have a spherical shape. Okay, you can have a sphere. And then you can have a cube. Okay, a cube-like object also can. So this is a volume. Okay, so volume expansion, it could expand in a volume as well. Okay, so the equations, again, you have the same equation, but with a different symbol. Okay, they are all being written in the same form. Okay, same form. So if you want to calculate the change in volume, delta V is equal to, now you use gamma. Gamma is the coefficients of volume expansion. So gamma and then V initial, delta T. So if you want to calculate the final volume, then V equals to V initial, bracket, 1 plus gamma, delta T. Okay, so they all looks alike. The difference would be in terms of the symbol. Okay, linear you use L, area you use A, volume you use V in the equations. And another main difference between these three given scenario situation is the coefficient. Linear, you use coefficients of linear expansion, which is alpha. Area, you use beta. Volume, you use gamma. Now, what is the relationship then between alpha, beta, and gamma? Well, from alpha to beta, or the relationship between alpha and beta is that beta is equals to 2 alpha. Okay? Whereas, okay, from alpha to gamma, okay, the relationship between gamma and alpha is that gamma equals to 3 alpha. So make sure you have these two equations, because these two equations, they are left out, okay, from your notes. Your notes, they didn't include these two, beta and gamma, the relationship between beta alpha and gamma alpha. So make sure you write it down. So now let's see how to solve questions 1. Questions 1, a steel ball has a diameter of 1.7 cm at 27 degrees C. Given that the coefficients of volume expansion for steel is 3.3 times 10 to the power of negative 5 degrees C negative 1, calculate the diameter of the steel ball at the 77 degrees C or at the 56 degrees C. Now, if you look at these questions, you are given the diameter at a certain temperature, at a particular temperature, which is 27 degrees C. So now I'm going to take this as my initial information. Okay, this is my initial information. So questions want you to calculate the final. Okay, this is a final at a 70 degrees C and also final at a negative 56 degrees C. So basically, you just have to repeat the same things for twice. Now, the questions would be, how are you going to calculate it? Okay. So if you look at the questions, this question is a bit tricky. Why? Because questions give you diameter. So like I told you just now, diameter is under linear expansions category. Okay, it's the forms of linear expansion. But then questions give you the coefficients of volume expansion. It gives you gamma. So which means you cannot use this value. Okay, this value is gamma. You cannot use it. You need to change it into alpha. All right. So let us begin with the coefficients of expansion first. So we know gamma is equals to 3 alpha. So alpha is equals to 1 over 3 times gamma, which is 3.3 times 10 to the power of negative 5. Therefore, alpha is equals to 1.1 times 10 to the power of negative 5 degrees C negative 1. Okay, so this is how you calculate alpha. So don't be fooled by the questions. Questions like to give you expansion for different cases. Okay, now questions will give you a linear expansion situations, but it likes to give you area coefficients of area expansions or coefficients of volume expansion. So from there, you need to know how to calculate the coefficients of linear expansion. All right. So you are given diameter. So diameter is a form of linear expansion. So make sure you use alpha. Okay, make sure you use alpha. So now I want to calculate final diameter because it asks you to calculate the diameter of the steel ball at 77 degrees C. So this is a final value. Oops. Okay, this is a final value. Therefore, I'm going to use the equation for final value, which is this one. Okay, L equals to L naught 1 plus alpha delta T. So in this case, I'm going to use symbol D because you're looking at diameter. So D equals to D initial 1 plus alpha delta T. So D final is the values that I want to calculate. So D initials given 1.7 cm. So you can keep it as cm, then your final answer will be in cm, all right? So 1.7, and then 1 plus alpha is 1.1 times 10 to the power of negative 5 times delta t, okay, times delta t. So what is the values of delta t? So initial temperature is 27, final is 77. So 77 minus 27. Okay, 77 minus 27. So eventually you obtain D equals to 1.701 cm. Question questions B. Okay, questions B, the tricky part is a temperature. Okay, so again, I'm going to use D equals to D naught and then 1 plus alpha delta T. But now, okay, now the equation is 1.7, 1 plus, again, this is 1.1 times 10 to the power of negative 5. But now the delta T. The delta T final is negative 56. So even though negative 56 is smaller than 27, but now this is your final temperature. So negative 56 minus 27. Okay, therefore you have 1.698 cm. Okay, 1.698 cm. So this is how you solve it. All right, this is how you solve it. Okay, so yeah, that is your questions one. So I give you 2 minutes to write it down. Okay, now including the summary, now I give you 4 minutes. Okay, I give you 4 minutes. So the summary, you can write it down. And then these two solutions, okay, especially how to determine alpha, make sure you know, okay, make sure you take a notes there. So 4 minutes for you to write it down, and then we'll proceed to questions number 2. If you are done, you may try questions 2. Okay, if you are done, you may try questions 2 first. Okay, so now let's look at questions 2. So question 2 is a very interesting questions. Now, what happens in questions 2? Yeah, where's those? Okay, here. Okay, so what happened in questions 2? Basically, you have a steel ball that has a diameter of 0.9 cm and a diameter of a hole in an aluminum plate. So now you have a ball, okay, with a diameter equals to 0.9 cm. And then you have a metal plate right here. Okay, so this metal plate. And then it comes with a hole as well. Okay, it comes with a hole. So this hole, okay, this hole, the diameter is 0.8990 cm. So calculate the temperature of the steel ball when it just passed through the hole if both ball and plate they are heated at in the same time. So now initially both of them, okay, now if you look at the diameters given, diameter of the steel ball is larger than the hole. So means that this ball it cannot pass through the aluminum plate. Okay, so it can only pass through if both of their final diameters is equal. Okay, it is when your D steel ball is equals to the D of an aluminum hole. Okay, otherwise it cannot pass through it. So this is the condition. Okay, this is the condition. Then we can try to start to solve it from here. So ds equals to dA. Now we are looking at the final diameter. Therefore, we apply the equation for the final linear linear expansion. Okay, the length of the final linear expansions. So ds equals to dA. Since you are looking at linear, so I'm going to use the first equations right here. Okay, the equation for the linear expansion. So ds is then equals to ds naught, okay, the initial value, and then bracket 1 plus alpha, okay, alpha for what? Alpha for the steel ball, alpha s, okay, alpha s, and then delta t, so t final minus t initial. Okay, so T initial given here is 20 degree. So we want to find out what is the final temperature. Okay, so T final. So you don't have to include the S here. Why? Because both of them, they begin at the same temperature and then they will end at the same temperature. So it is equals to dA initial, which is 0.8990 cm, and then bracket 1 plus alpha. Alpha for what? Alpha for aluminum, alpha A, and then T final minus T initial. Okay, so the part that you have to take note is the alpha. So different materials, they have different coefficients of linear expansion. So now you can expand the equation. So DSO is your 0.9 bracket 1 plus alpha for steel given is 1.1 times 10 to the power of negative 5. Temperature, now T final, we don't know. So minus T initial 20 degrees C. Okay, and then it is equals to aluminum initial diameter is a 0.8990, and then 1 plus alpha for aluminum 2.2 times 10 to the power of negative 5, right? And then T final minus 20 degree. Right, so rearrange the equations. Eventually, you will obtain T final equals to 121 degrees C. So at this temperature, okay, at this temperature, the ball, the diameter ball, the steel ball would be able to pass us through the hole. Okay, because now that they have the same surface area, same diameter. Okay, same diameter. So this question, it makes sense. Why? Because if you look at the questions, alpha for steel is less than alpha for aluminum, which means aluminum will expand faster than the steel ball. So the hole will get bigger, bigger at a faster rate compared to the steel ball. Therefore, at the temperature T equals to 121 degrees C, the hole will have the same diameter as the steel ball. Okay, so kamu tengok alpha. Alpha untuk aluminium lagi besar daripada alpha steel. So aluminium plate dia punya lubang akan jadi lagi besar, lebih cepat. Okay, akan jadi besar lebih cepat berbanding dengan bola. So at a temperature 1 to 1 degree C, the ball will be able to pass us through the hole. All right. So now I give you 2 minutes to write it down. Okay, then you can make a short notes there. Why the ball can pass us through the hole at 1 to 1 degree C. Okay, that is because of the alpha. Okay, that is because of the alpha. So this type of explanations you need to know because it can be asked in the exam. Okay, sometimes the questions will ask you why. Okay, why the ball can pass us through the plate at temperature 1 to 1 degree C. Then you need to be able to explain. That is because of the linear expansion, the coefficients of linear expansion, the alpha. Okay, the alpha. So you make a short notes there. Okay, I give you 2 minutes to write down the answer and also to write down the justification. Okay, the explanation. All right. Okay, so next, questions number 3. Okay, questions number 3, a 50 cm cube brass container full of a glycerin at 30 degrees C. When the temperature of the container rises to 40 degrees C, how much of the glycerin spill out? Okay, and explain why is there an overflow. So you see, the questions will ask you why. Okay, why? So you need to be able to explain. So in a linear expansion, in a question just now, you explain it based on alpha. In these questions, you can explain it based on the gamma. Okay, because now you're looking at volume. So how do I know that it's volume? By looking at the unit. You have a 50 cm cube. So now you have a unit in terms of cube. So how are we going to solve these questions? How much of the glycerin spill out? So if you want to calculate the overflow, okay, so V overflow is equals to V final of the liquid. So liquid is glycerin, G, okay, minus the V of the container, which is the brass container, B. Okay, so Vg minus Vb, in which it means we need to calculate, okay, we need to calculate delta V, delta V. You want to calculate the volume, the change in volume, the overflow. So delta V minus the delta V over G, Vg minus delta Vb. So why? Okay, why I use delta V but not the V? Okay, because if you look at the container, initially this is a container. Okay, now it's full with liquid. Okay, so it's num right here. Right, so if you calculate the change, then you will be able to calculate the overflow. Okay, you'll be able to determine the overflow. Well, if you want to calculate final, actually also can, okay, because they have the same initial. So if you calculate the final, you subtract them, you should be able to obtain the same answer. So you have two choices, okay, you have two choices. It's up to you whether you want to use a change or you want to use final, since they have the same initial, okay, since they have the same initial. Okay, now let's see, okay, in these questions, it means you need to calculate delta Vg. So delta Vg, it's equals to, okay, now gamma G glycerines times the Vg initial, okay, and then times the delta T. So this is the equations that we're going to use. So it is then equals to, now glycerine is a 49 times 10 to the power of -5. Initial's volume is a 50 cm cube. So 50 cm cube is 50 times 10 to the power of -6 meter cube. And then the change in temperature, now from a 30 degree to 40 degree. So 40 degree is your final temperature, 40 minus 30. All right. And then it is equals to, if you calculate the overflow, it should be 2.8 times 10 to the power of -8 meter cube. So this is the change in volumes of the glycerine. Right, now I'm going to repeat the same thing for the container. So VB equals to gamma B and then B initial times delta T. Okay, now if you look at the questions, once again you're given alpha, and now we are looking at volume. So you need to know that gamma is actually equals to 3 alpha. So these equations can then be rewrite as 3 alpha B VB initial delta T. Okay, so it is then equals to 3 times 1.9 times 10 to the power of -5. And then the initial again is 50 times 10 to the power of -6. Change in temperature 40 minus 30. So it is equals to 2.45 times 10 to the power of -7 m cubed. Okay, m cubed. Wait, I got the, I write the wrong value. So this one and this one, terbalik. Okay, so Vg, I have 2.45 times 10 to the power of -7 meter cube. Container, I have 2.85 times 10 to the power of -8 meter cube. Right? So the crucial part is here. Okay, most of the time students got it wrong because of the careless mistake. So make sure you read the questions carefully. See the values given is for which type of expansion. So you're given alpha, this is for linear expansion. And now we are doing volume expansion. Therefore, make sure to convert it into gamma. Okay, so gamma is equals to 3 alpha. This is very important. So now that you have both delta Vg and delta Vb, you can then calculate the overflow. Okay, so overflow is equals to 2.45 times 10 to the power of -7 minus 2.85 times 10 to the power of -8. So it is equals to 2.165 times 10 to the power of -7 meter cube. Okay, 2.165 times 10 to the power of -7 meter cube. So be careful with the power. Okay, one is -7, one is -8. Make sure you key in the right value when you key in into the calculator. Okay, when you use calculator. So this is also another very common sin mistake. Okay, kedua-dua ada power yang tak sama. Satu -7, satu -8. So make sure you have the right power. So questions B, explain why. Why is there an overflow? Because gamma glycerine, okay, gamma of a glycerine is larger than the gamma of the brass. Okay, therefore glycerine will expand faster than expand. Okay, it expand more. Okay, expand more than the brass container, more than brass container when heated. Okay, when heated. So that is the explanation. So you look at the coefficients of expansion. Okay, if you are doing a linear expansion, then you compare the linear expansion's coefficients. If you are doing a volume expansion, then you compare the coefficients of volume expansion. That's it. Okay, it's very simple. If you understand the meanings of the coefficient, then you should be able to answer most of the explanation questions, right? So that is the answer for questions number 3. And again, I give you 2 minutes to write it down. Okay, 2 minutes to write it down, write down the solutions, and also write down the explanation. Okay, you need to know how to explain it. So 2 minutes for you to write it down before I proceed to the next questions. All right, now let's look at the next question. Okay, so we have 3 more questions. Okay, let's see if we can finish it today. So a glass flask whose volume is 1000 cm cube at 0 degrees C. It's completely filled with mercury at this temperature. When the flask and the mercury, they are warmed to 100 degrees C, 15.5 cm cube of the mercury overflow. If the coefficient of volume expansion of a mercury is 18 times 10 to the power negative 5, determine the coefficients of volume expansions of the glass. Okay, so according to the questions, now you have an overflow that is equals to 15.5. Okay, 15.5. So questions ask you to calculate the change in the coefficients. Okay, ask you to calculate the coefficients of the volume expansions of the glass. So basically, the idea is very similar to the question just now. Okay, to the previous questions. What you have to do? Okay, you just reverse the process. So you're given a delta V overflow. It is equals to 15.5 times 10 to the power of negative 6 meter cube. All right. And now we know that delta V overflow is equals to, now you have a glass flask, and also a mercury. Okay, and you want to calculate overflow, so it should be delta V mercury minus delta V of the flask. Okay, because flask expands slower than the mercury. That's why overflow happened. So now next things, what I want to calculate, okay, since I want to calculate the coefficients of volume expansions of the glass, so which means I need the gamma, okay, I need to have the gamma in my equations. So if I expand this equation furthermore, okay, I will obtain 15.5 times 10 to the power of negative 6 equals to delta Vm. So what is the equations for delta Vm? It is gamma m, which is the values that I want to determine. Expansion of the glass. Okay, so this is the values given, sorry. So your given 1.8. So delta m, and then your volume for m initial times with the delta t. Okay, and then minus gamma of the flask, and then V flask initial, and a delta T. Next step, I'm just going to expand it. Okay, I'm just going to expand the equations. So 1.5 plus 15.5 times 10 to the power of negative 6 equals to, now gamma m is given. It is 18 times 10 to the power of negative 5, and then times with the Vm. V given 1000 times 10 to the power of negative 6. Change in temperature from 0 to 100 degrees. So 100 minus 0 minus gamma of the flask. Initial value is the same, 10 to the power of negative 6. And then change in the T is also the same, 100 minus 0. Rearrange the equations. You should be able to obtain gamma for a flask. Okay, the volumes, the coefficients of volume expansion of the glass is equal to 2.5 times 10 to the power of negative 5 K negative 1. Okay, 2.5 times 10 to the power of negative 5 K negative 1, which makes sense because mercury has a higher gamma compared to the glass. That's why overflows happen. Okay, that's why you have overflow. So if you obtain gamma flask larger than gamma mercury, it means something is wrong in your calculations. Okay, something must be wrong. Because if gamma of the glass is less than gamma of the mercury, then overflow won't happen. Okay, there will be no overflow in these situations. So I give you 1 minute to write it down, okay, because this is very similar to the previous questions. So 1 minute for you to write it down, then we will proceed to the next one. Okay, we'll proceed to the next questions. Okay. Next. Okay, next again we have the questions. Okay, I have the questions in volume expansions. Okay, related to volume expansions. Okay, yeah, where's the okay. All right. Okay. So the 70-liter steel gas tanks of a car is filled, okay, to top with the gasoline at a 20 degrees C. The car sits in the sun and the tank reaches a temperature of 40 degrees C. How much of a gasoline do you expect to overflow from the tank? So basically, again, it's a question for overflow. Okay, it's a question about overflow. So basically, we can just repeat the same method. All right. So against delta V overflow is equals to the delta V of the gasoline minus delta V of the tank. So these questions, I will leave it to you as an exercise, right? So basically you have the same method, exactly same as the previous questions, okay? The questions number 3. So this one, I will leave it to you as an exercise. Now let's see questions number 6. So questions number 6, a hollow aluminum cylinder has an internal capacity of 2000 cm3. It is completely filled with a turpentine at a 20 degrees C. Okay, so if both of them, their slowly warms together to 80 degrees C, how much overflow? Okay, and what is the volume remaining in the cylinder at 80 degrees C? So now you heat it up. Okay, so we heat it up, and then let's see what is the final volume. So it's actually asking for two different things. Okay, it's asking for the overflow, and it is also asking for the final volume. Okay, for the final volume. So let's see how to solve these questions. So overflow, now since we want to calculate the final volume, okay, this is final volume. So let us use V overflow, okay, V overflow equals to VT minus V aluminum cylinder, okay, VC, okay, VT minus VC. So I'm going to use final volume to calculate overflow right now. Why? Because question is asking for final volume. So to make it easy, okay, to make it easier, I don't want to do the same calculation twice. Okay, instead of calculating the change in the volume, I will straight away calculate the final volume. So V final for turpentine is equals to V initial bracket 1 plus gamma T delta T. Okay, it is then equals to, well, initial is 2000. Okay, I'm just going to keep it at a cm cube. So 2000, 1 plus 9 times 10 to the power of negative 4 temperature. So initial, final is 80. So 80 minus 20. Okay, it is then equals to 2108 cm cube. Okay, so this is for questions A. And then VC is equals to VC initial 1 plus gamma C delta T. But again, if you look at the questions, you are given alpha, okay, you are not given gamma. So these equations can then be rewrite as VC naught 1 plus 3 alpha C delta T. Okay, so therefore it is equals to, again, is 2000, 1 plus 3 times 24 times 10 to the power of negative 6, and then times 80 minus 20. Okay, so the final volume is 2008.64 cm cube. Therefore, the overflow is equals to 2108 minus 2008.64. So overflow is equals to 99.36 cm cube. Now, questions B. Okay, let's look at questions B. Questions B is a bit tricky. It asks you the final volume of the turpentine. Okay, so the final volume remaining, if you look at the keywords, remaining in the cylinder. Therefore, you shouldn't use V final for turpentine. Okay, you should use the V final of the container. So therefore, the answer would be 2008.64 cm cube. Okay, not 2108. 2108 is the total volume, including the one that is the overflow. All right, but now the question is asking for the one remaining in the cylinder. So you need to use V final for the cylinder, right? Because it's remaining. It is not asking for the actual final volume. Okay, it is asking for the remaining volume. So that's it. Okay, that is the answer for questions number 6. And I think that's all for today. So if no questions, okay, after you write it down, you may leave the class. Remember to do questions 5 as the exercise. Okay, remember to do questions 5 as exercise. So that's all for today, right? So after you